Welcome back everyone. Last time we used triangles to solve integrals with square roots. And today instead we are dealing with pure trigonometric chaos, integrals with powers of sine and cosine. Specifically, we're going to look at integrals of the form sine of x to the power j times the cosine of x to the power k. It looks scary, but there is a secret. You only need to check one thing. Is at least one of the two powers odd? Let's look at the general technique. So, here's the game plan. In case A, one of the two powers is odd, then we are lucky. Indeed, if j is odd, we use a u substitution u equal to the cosine of x, and if k is odd, instead we use the u substitution u equal to the sine of x. If both of them are odd, we can do exactly whatever we want. At the end, then we have to substitute in the result the fundamental relation, sine squared plus cosine squared equal to 1, and then we are ready to integrate explicitly our integral. In case B, instead, both powers are even. And here instead we have to work a little bit more. Indeed, there are two possible scenarios. Or we use the alpha-angle formulas, so sine of x squared equal to 1 minus the cosine of 2x over 2, and the cosine of x squared is equal to 1 plus cosine of 2x over 2. And then we have to go back. So, or we can integrate it explicitly using again the odd method that we have seen before, or we have to use again the alpha-angle formulas. We can also be lucky and we can just have to explicitly integrate it. But let's go with some examples. Let's start with something easy. Here we have the integral of the sine of x times the cosine of x to the power 3. And both powers of the sine and cosine are odd. Indeed, I can think the sine to be to the power 1. And 1 and 3 are odd. In this case, what we can do, well, we have multiple choices. For example, we can set up u to be equal to the sine of x. And then we get that the du is equal to the cosine of x dx. And so now we are almost ready to do all the substitution. Indeed, here the sine of x is going to be equal to our u. One of these cosine is going to go away with a differential. What to do with the remaining part? So what I mean by that, I mean that we can rewrite this integral directly as the integral of the sine of x times the cosine of x squared times the cosine of x dx. So now this cosine of x in dx will go away with a differential, and the sine of x is going to go out with u. So we are left with the cosine of x squared. How can we take care of that? Well, we can use the basic trigonometric identity. Indeed, we know that 1 is equal to the sine of x squared plus the cosine of x squared, which means that the cosine of x squared is equal to 1 minus the sine of x squared. Now, why is it useful? Well, first things first, now we have expressed the cosine squared in terms of the sine of x, and our change of variables is really good to substitute u with the sine of x. So if we combine this identity into this integral together with this change of variables, we can actually simplify the integral drastically. Indeed, let's make a step in between. The integral over here can be rewritten as the integral of the sine of x times 1 minus the sine of x squared times the cosine of x dx. And now the change of variable becomes quite simple. Indeed, the sine of x becomes u, the sine squared of x becomes u squared, and the cosine of x dx is just my differential, du. So we are left to compute the integral of u times 1 minus u squared du, which we can rewrite as the integral of u minus u to the power 3 du, which simply becomes u squared over 2 minus u to the power 4 over 4 plus a constant. And then I do have to remember that u is equal to the sine of x, so this one becomes the sine of x squared over 2 minus the sine of x to the power 4 over 4 plus a constant. Now let's focus on an example with the even power. Here we have the integral of the sine of x squared, and 2 we all agree is even, and since the cosine is not there, I think I can think of having here the cosine of x to the power 0, and 0 for the sake of being even or odd, we are going to consider it to be even if it's not really precise. So now, how do we solve this integral? Well, in these cases, we remember that if both of the powers are even, we have to use the double angle formula to simplify this expression into something containing only the cosine of 2x. So let's start with the identity. So we do remember that the sine of x squared is equal to 1 minus the cosine of 2x all divided by 2. Now, 2 minutes for all of you that have a memory of a fish, and like myself, because I don't remember these formulas, okay? I never do because they are like too complicated and my brain power is basically 0. But what I do remember is the following. I know that the cosine of 2x is equal to the cosine of x squared minus the sine of x squared. And now I can use the fundamental identity on the cosine of x to rewrite the right hand side as 1 minus 2 times the sine of x squared. And now from this identity here, I can reconstruct this one by bringing the sine on the other side, the cosine on the other side, and then divided by 2. Okay? So don't panic if you don't remember this identity. Okay? So now let's get rid of this because we don't need it right now. So using this identity, we can rewrite the integral as the integral of 1 minus the cosine of 2x all divided by 2 in dx. Great, and now we are basically ready for the integration. Indeed, we can simplify it as the integral of 1 over 2 minus the cosine of 2x divided by 2 in dx. And now this is equal to, so the integral of 1 over 2 is just x over 2 minus, and now we have to do a little bit of trickery here if you don't do the explicit substitution. But so we first remember that the integral of the cosine is the sine of x. And then you see that here inside the cosine we have 2x. So we have to divide everything by 2 to get rid of the composition factor. Which means that this integral becomes sine of 2x divided by 2 times 2, so divided by 4, plus a constant. And that's it. Now, as always, the exercise which is a little bit more difficult than all the others, with a little trick. So here we have to integrate the sine of x to the power 2 times the cosine of x to the power 2. So 2 even power. So we should get ready to do all the reduction, okay? So in principle, we can do this substitution, so we can write down the sine of x squared as 1 minus the cosine of 2x divided by 2, and the cosine of x squared as 1 plus the cosine of 2x divided by 2. But this is like not that good actually, because what you're gonna do is say, well, now I have these two guys, I have to put them back, and I'm gonna get again the cosine of 2x squared, so I have to simplify them out again. But there is a slightly faster way of dealing with this integral, which I think you will like. So let's erase this because we are actually not going to need it. But we're going to need the following formula actually. You remember that the sine of 2x is equal to 2 times the cosine of x times the sine of x. You say, great, yeah, I know that. Well, stay with me. Let's simplify the 2 on both sides. And now we get the sine of 2x over 2 is equal to the sine of x times the cosine of x. Let's get rid of these 2. How can this be helpful? Well, we can actually write all the integral as the integral of the sine of x times the cosine of x, all to the power 2 in dx. And now we know that the cosine of x times the sine of x here is equal to the sine of 2x, which means that I can rewrite this integral as 1 over 4 the sine of 2x squared dx. Okay, and now there is really no other trickery involved. It's actually the time for us to do the double angle formula and write it down in terms of the cosine of 4x, actually. So before doing that though, let's write it down as 1 over 4 times this integral, so the sine of 2x squared dx. Oh, wait a minute. If I do this substitution, 2x equal to t, what do I get? Well, if I do that, now I have the 2 dx is equal to dt. I can simplify the 2 on both sides, and now I can rewrite this integral as 1 over 4 times the integral of 1 over 2 times the sine of t squared dt, which again I can rewrite as 1 over 8 times the integral of the sine of t squared dt. Wait a minute. This integral looks familiar. We just did that. So if you go back, I'm gonna slide a little bit up. We computed that the integral of the sine of x squared is just equal to x over 2 minus the sine of 2x over 4 plus a constant. Well, let's just copy this, because that's what we're actually gonna need. Well, I'm gonna put it here. So now, using this formula, I can integrate this factor. So this is gonna become 1 over 8 times, instead of x I have t, so this is t over 2 minus the sine of 2t over 4 plus a constant. And now I do remember, so first I'm gonna move this here. Now I do remember that t is equal to 2x, which means that this integral becomes 1 over 8 times x minus the sine of 4x over 4, everything plus a constant. Why I can pull up the constant? Because here we'll get the constant divided by 8, but a constant divided by 8 is still going to be a constant, so it doesn't really matter. So, to summarize, odd powers are your best friends. You can just integrate them directly, basically. Even powers, well, you have to work a little bit and use the alpha angle formulas until they disappear, or you can try to use my trick. In the description, you will find a link to the GitHub repository where you find all my cheat sheets. And also there is a new one just dealing with this technique. I'll see you next time!